Hello, this is the second episode of the Pythagorean Theorem series. In this second lecture, we are going to discuss a new approach to proving the Pythagorean Theorem. What will be discussed? First of all, we will show you that the geometric series can be used to compute the length of a line segment and the area of a shape. Similarity and the scaling factor induced from similarity are used. Then a new approach will be developed for proving the Pythagorean theorem using this technique. We are able to reprove some old proofs in Loomis' well-known book. With the help of the Lemoine, Grebe, or Symmedian point, a new proof will be discussed. So, let's review the similarity concept and the scaling factors. Given a line segment AB and a point Z there, how do we calculate the length of xy? For convenience, let's say xy is named as A. xz is named as A minus B, where B is the length from Z to Y. If we know the ratio of B over A, the length of A can be computed with the ratio and the length of A minus B. Of course, what are known includes the length of A minus B and the ratio of B over A. So let the ratio of the length of B and over A be rho less than 1. Of course, rho must be less than 1 because rho is the length of B over the length of A. So rho is defined in this way. Therefore, the length of zy, that is the length of B, is simply rho times the length of A. In other words, this expression states that we shrink the length of xy by a factor of rho to the length of zy. Therefore, this factor rho, or the ratio rho, is referred to as the scaling factor, going from xy down to zy. Now, let's rewrite the whole thing. The result will be obvious. We know xy is equal to zy here plus xz. But we do know the length of xz. So xz here, but zy is reduced xy. That is, zy is equal to rho, the scaling factor, times the length of xy. However, the length of xy is the sum of xz plus zy. So this term becomes rho times xz. This term becomes rho times zy. But as we used here, zy is reduced from xy by a factor of rho. Therefore, zy is rho times xy. This one becomes xz plus rho xy plus rho squared times xy. But again, xy is the sum of xz plus zy. Therefore, we have a term rho 2 times xz and rho 2 times zy. Repeating this process indefinitely, we have xy is equal to xz plus rho times xz plus rho squared times xz plus rho to the cube times xz and so on. So we can take xz outside of this expression. So this one becomes xz times the sum of 1 plus rho squared plus rho to the cube plus rho to the fourth power and so on. And as you know, this is a geometric series. The sum is 1 over 1 minus rho. Therefore, the length of xy, given the scaling factor rho and the initial part a minus b, xy is calculated as 1 over 1 minus rho times xz. So this is the way of knowing the length of a minus b and the scaling factor can help us calculate the length of the whole segment. And this is the linear case. For area, that is a two-dimensional shape. So given a shape A, how can we calculate this area? By the same concept, we find a figure B that is similar to A. So we have shape B here. Outside of B and inside of A, we have A minus B. We shall use A of x to denote the area of x. So the area of B and the area of A satisfy this. That is, the area of A is the sum of the area of B plus the area of the complements of B, and that is A minus B. Now, because A and B are similar, any edge of A, we assume that A and B are polygons. Any edge E of A and its corresponding edge F in B satisfies this. That is, we scale the edge E by a factor of rho down to F. Of course, rho is less than 1. This rho is also called the scaling factor from A going down to B. Because area is a 2D object, the scaling factor for area is rho squared. If we know rho is a scaling factor of an edge, more precisely, we know the area of B is equal to rho squared times the area of A. So apply the same idea. We work for the linear case. The area of A is the sum of A minus B plus area of B. But area of B is rho squared times area of A. But A is the sum of these two. So we have rho squared times the area of A minus B plus rho squared of B. Continuing this, we have the area of A is the sum of this. Now, the only difference between this and the linear case is, in linear case, we have rho here, rho squared, rho to the cube, and so on. But now for area, it's rho squared, rho to the fourth power, rho to the sixth power, and so on. This process, of course, can continue. So we eventually have an infinite series, which is geometric, because rho squared multiplied by rho squared will have fourth power, multiplied by square will have sixth power, and so on and so forth. Therefore, according to the geometric series property, the area of A is 1 over 1 minus rho squared times the area of A minus B. The only difference is square here. A quick summary. Here, indicates that if we know the scaling factor and the complements of the set B or the shape B, the area of A can be calculated easily. So what we have to do is, given a shape A, we need to find a B that is similar to A inside A. And then from the edge A here and the edge B here, we find rho. So rho is the ratio of an edge here and the corresponding edge here using the linear case. Then compute the area of the complements. Then the area of A is this. So it's pretty easy to do. Now, let's use a very simple notation. S sub rho indicates that the shape X is reduced to Y by scaling it down by rho linearly. And if there's a square, it means we are scaling down by square. So this is A, this is B, and both are squares. The yellow area is A minus B. And then we take B out. That is A is scaled down to B, let's call it B sub 0, by a scaling factor rho. So this one is similar to A, becomes this. And then we take a look at this one, that B0. We find the similar shape here and similar to the outer one. So this one is scaled down from A by rho twice. We have B1. This B1, the same similarity configuration, we have B2. B2 is scaled down 3 times from A by a scaling factor rho. So this is B2, and this is B3, and so on. And eventually, we apply the same configuration, A inside the B. We have B. We consider this B as a new A, and this one is the scaled down B. And let's say this is A, then this one is scaled down B. And if we consider this one as A, then this one is a scaled down B. So this process can continue indefinitely. And that's the idea of calculating area by the use of geometric series. So what did we learn? Given a line segment xy and a point z in xy, if rho is the scaling factor of reducing xy to zy, and we know how to compute the length of xz, then xy is this. Replacing segment by shape, then we have this. Given a shape A and the shape B inside A, and it is similar to A. If rho is scaling factor of reducing A to B, and we know the area of A minus B, then the area of A is this. So linear, two-dimensional, linear, two-dimensional, linear, two-dimensional. Then we're going to apply this idea to prove some examples. These examples are taken from Loomis' book, as we discussed in our first episode. These proofs are quite simple. The given rectangle of side lengths are A, B, and C. A, B, and C. We can construct a square of length A plus B. So in this case, A is the square of side length A plus B. And because the right triangle, the given one is AB, and C is its hypotenuse. Therefore, the inside of A we have a square B, whose side length is C. Therefore, in this case, B is this inner square. A minus B is the sum of these 4 right triangles. The scaling factor is simple. Because this is a square similar to the outside one, This square has length c. This square has length a plus b. Therefore, rho is equal to c over a plus b. Some calculation yields 1 over 1 minus rho squared is this. The area of a minus b is 4 times the area of this right triangle, which is a times b divided by 2. Therefore, the area of a minus b is 2 times a times b. The area of a, according to our method, is 1 over 1 minus rho squared times the area of a minus b. But square a can also be calculated as a plus b squared. So the result of this method and the result of our method must be equal because we are calculating the same area. So simplify this, and further, we are able to cancel 2 times a times b. Because of this, we get c squared equals a squared plus b squared. We get our results. Now consider a second example. This time, we use c, the hypotenuse length of the given right triangle, as the side length of the square. And the right triangle is flipped inside. A here, B here. So these 4 right triangles are congruent. Inside of A, we have a square. Again, the length of this square obviously is B minus A. B of this one and A of this one. So immediately we know the scaling factor rho is B minus A over C. Therefore, 1 over 1 minus rho squared is this. The area computed with this new method is, this is 1 over 1 minus rho squared, and this is the area of A minus B, the outside area. The area of the outer square is also c squared. So c squared must be equal to the results we computed. Then simple simplifications. We get that. We have 2 examples, commonly seen examples, which were also discussed in Loomis' book, proved with our method. Now let's take a look at another simple one. We have a right triangle ABC with A length B and the hypotenuse length C. We construct a perpendicular from C to the side BA with perpendicular foot D. For convenience, the length of CD, that is the altitude on the hypotenuse BH, and the length of BD, BK. So here, the area A is the big one. The smaller area is triangle ADC. So A minus B is the triangle CBD. Now, what is rho? Because this triangle and this triangles are similar. So the shorter non-hypotenuse leg for area B is H. The shorter leg of triangle ABC is A. Therefore, rho is H divided by A. What we need to do is finding out what H and K are. Because triangle CBD is similar to triangle ABC. We have H over B is equal to A over C. Notice here, B is the hypotenuse length of triangle ACD. By the same reason, we have K equals to A squared divided by C. Therefore, rho is equal to h divided by a, which is equal to b over c. As a result, 1 over 1 minus rho squared is this. The area of CBD is h times k divided by 2. So area CBD is this. Plug in the value of h, the value of k, we have this. Therefore, the area of ABC, according to our method, is the area of the complement times 1 over 1 minus rho squared. So we get this. After some simplification, we have this. This is the area of triangle ABC calculated with our method. However, the area of ABC is also a times b divided by 2. That is obvious. These two areas must be equal. Then, after very simple simplification, we have the Pythagorean Theorem. So, we finish the third example with our method. Now, the fourth one is not taken from Loomis' book. Instead, it could be considered as an extension of example 3. So, what we need to do is construct a perpendicular from D to side AC, meeting the side AC at E. We have already named CD as H, BD as K. Now we name P to be DE, Q to be CE. Because the triangle ADE is similar to the triangle ABC. Therefore, rho is simply P over A. Now, what is P? We find it out. Triangle CDE is similar to ABC. Therefore, P over H is equal to B over C. Therefore, P is H times B over C. Because we know H is equal to A times B over C, we have P this. Now, because Q divided by P is the same as A divided by B due to similarity, therefore Q is this. P times A over B, and we know P here, so Q is this. Therefore, rho is P over A, we have this. Rho is B squared divided by C squared. As a result, 1 over 1 minus rho squared is this, a little bit more complex. The area of BCED, which is a trapezoid, is this. So it's the sum of this P and the A multiplied by the altitude divided by 2. So plug in the value of P and Q, we have this. Some simplification yields this. According to our method, area ABC is 1 over 1 minus rho squared multiplied by the area of A minus B. After some simplification, we get this. Because the area of ABC is also A times B divided by 2. So this is the obvious method result. And this is our method. Simplification yields this. I found this configuration from a website called Cut Knot. But why I put it in as a example 4? Because it is the same as applying example 3 twice. The first one, A is here, B is here. And then we use this one as B and this one as A minus B. So example 4 is an integration of two applications of example 3. Example 5 is an example from Loomis' book. This is the proof number in Loomis' book, and this is the page number. This one requires some construction. We have the right triangle ABC. We extend the hypotenuse C to a point D, so that BD is equal to BC. From D, we construct a perpendicular to AB, meeting the line AC at E. So we have two congruent triangles, EDB and ECB. You can easily prove it because we have two sides equal, and the common side and the right triangle, a right angle. Therefore, this P is equal to this P. Currently, we could use A as this big triangle, B as the given smaller triangle, and A minus B is this quadrilateral. What we need to do is calculate the area of this quadrilateral, ECBD, and calculate the scaling factor rho, which is pretty easy because this side, AD, after applying this rho, we get A. Therefore, rho is simply A over P. But what is P? Because triangle ADE is similar to the triangle ACB. We know rho is equal to A divided by P. Due to similarity, the ratio of this side is equal to the ratio of this side and this side. So rho is A over P, which is equal to A over this. After simplification, we have this. Therefore, 1 over 1 minus square is this. The area of CBDE is twice of the area of this. The area of this is A times B divided by 2. We have this. Finally, let's take a look at the area of the triangle ADE. According to our method, it is 1 over 1 minus rho squared multiplied by the area of CBDE. So this is the CBDE area. This is 1 over 1 minus rho squared. After some simplification, we have this. However, the area of ADE can also be computed as P times A plus C divided by 2. Plug in the value of P computed in the previous slides, we have this. Because these two expressions are for the same area, that is the area of triangle ADE, they must be equal. As a result, we can cancel a few terms like B and B here, and A here, A plus C squared, and A plus C to the cube here. A very simple simplification yields the Pythagorean theorem. Example 6 is a little bit more complex. Let's say ABC is a right triangle of side length ABC, with angle C being 90 degrees. Let's construct a square on the hypotenuse. Of course, this square side length is C. Let this square be A, B, B2, A2. Angle A is alpha, angle B is beta. Now let's extend the side AC, BC, and the side A2, B2 will have new right triangles. It is obvious due to parallel lines. Angle A1 is equal to angle A, which is alpha. Angle B1 is equal to angle B, which is beta. Now, what is this angle? This is 90 degrees, so this angle has to be beta because A plus beta is 90 degrees. Similarly, this angle is alpha because alpha plus beta is 90 degrees. Alpha plus beta is 90 degrees. So what we need to find out is the length of A1, A2, let me call it P, and the length of B1, B2, let me call it Q. Because the large triangle A1, B1, C is similar to the smaller triangle A, B, and C. We could use large triangle as A, the smaller triangle as B. So the remaining or the complement is a trapezoid. We call it A minus B. So what we need to do is calculate the area of this trapezoid. And rho. What is rho? Rho is C over P plus C plus Q. So the key is finding out what P and Q are. Now, because triangle A1, A, A2 is similar to the triangle A, B, C. Therefore, P over C is equal to B over A. And P is this. Similarly, we have Q, this. So the side length of A1, B1 is P plus C plus Q. This is P, this is C, and this is Q. The area of trapezoid A, B, B1, A1 is the top side plus the bottom side multiplied by the altitude. We have this. The scaling factor is C over P plus C plus Q. We have this. From here, 1 over 1 minus rho square is this. The term AB is cancelled out. Therefore, the area of A1, B1, C, according to our method, is 1 over 1 minus rho square times the area we calculated earlier. We have this. So these two terms cancel out. We have this. We need to calculate the area of A1, B1, C differently. We know the area of this right triangle is the product of CA1 and CB1 divided by 2. Because rho is the scaling factor, we multiply the scaling factor to the length of CA1, we get CA. Therefore, CA is B divided by rho. CB is equal to A divided by rho. The area of CA1, B1 is half of CA1 multiplied by CB1. So A divided by rho times B divided by rho, we have this. And this calculation here must be equal to the calculation we obtained earlier. So the cancellation is very obvious. These two terms are gone. These two terms are gone. These two terms are gone. So the remaining would be 1 here. Here is C squared over A squared plus B squared. So we learned 6 examples from very simple to rather complex. Now, I'm offering you a possibly new proof. I said possibly, it's because I don't know whether this proof was published or not, because the literature in proving the Pythagorean theorem is so huge. I won't be able to check for everyone. So in this case, let's introduce a very interesting concept. It's called Lemoine points or Grebe points or the Symmedian points. We have a triangle ABC. The incenter is the intersection points of the three angle bisector. So the incenter is angle bisector here. The centroid is the intersection point of the three medians. What is a median? A median is a line going from a vertex to the midpoint of this opposite side. So here, the centroid is marked in red. So on this side, median here. On this side, the median's here. On this side, the median is here. For each vertex, there is a median and there is an angle bisector. There is an angle between the median and angle bisector. How about we construct another line with the same angle like the angle between the median and angle bisector. So the angle here and the angle here are the same. Of course, the complement of this angle here and the complement of this angle here are also equal. So this can be constructed for every vertex. And this line, the newly constructed line, is called a Symmedian. That is symmetric to the median with respect to the angle bisector. Because a triangle has three vertices, and each vertex has a median and an angle bisector, of course, there is a symmedian for each vertex. These three symmedians are concurrent, that is, meeting at a point. So here, this symmedian is symmetric to this median with respect to this angle bisector. This symmedian is symmetric to this median with respect to this angle bisector. This symmedian is symmetric to the median with respect to this angle bisector. These three lines are concurrent, meeting at a point here, color in blue. This point is referred to as the Lemoine point in most French and English textbook literature, and the Grebe points in German, and also Symmedian point. We frequently use Lemoine points. This point is very important in the so-called modern triangle geometry. That is the Euclidean geometry studying triangles. How do we construct the Lemoine point? There are so many ways. You could construct it based on the definition. But the following one is very useful to our discussion. Given a triangle ABC, then for each side of this triangle, we construct a square outside of the triangle. Then the outer edge of the squares can be extended. They, of course, meet at a point A1, B1, and C1. And this triangle, the given one and the newly constructed one are similar, of course, because the sides are parallel to each other. Then we connect the corresponding vertices. We have A1A, B1B, and C1C. These three lines are concurrent, meeting at a point. Why? We're going to offer you a proof. Because the side of this triangle and this triangle are parallel to each other, so AC and A1C1 are parallel to each other. They meet at the point at infinity. Similarly, AB and A1B1 are parallel. As a result, they meet at a point at infinity. By the same reason, the side BC and the B1C also meet at a point at infinity. Because the intersection point of AB, A1, B1, the intersection point of AC, A1, C1, and the intersection of BC and B1, C1 are all at infinity, which means these three intersection points lies on the line at infinity, which means the intersection points of the corresponding sides of these two triangles are collinear, lying on the line at infinity. By Pythagorean theorem, the line connecting the corresponding vertices are concurrent. So we cited this theorem. We are not going to prove it because you can find it in nearly every geometry book. So the concurrent point is exactly the Lemoine point. We offer you another look at the Lemoine point, ABC. Let's say this is a Lemoine point. Let's construct a perpendicular from the Lemoine point to each side. The distance from Lemoine point to side A is PA. The distance from Lemoine point to side B is PB. And the distance from the Lemoine point to C is PC. One very important property of the Lemoine point is the ratio of A, B, and C is equal to the ratio of the distance from the Lemoine point to A, to B, and to C. Or if you like, the ratio of the distance from the Lemoine point to A over A is equal to the distance from the Lemoine point to B over B, and so on. This property can be used as a characterization of the Lemoine points. In other words, if a point satisfies this property, this point is going to be the Lemoine point of that triangle. If the triangle is a right triangle, things become easier. The Symmedian on the hypotenuse is the altitude on the hypotenuse. So you don't have to compute the Symmedian. We just drop a perpendicular from the 90-degree angle to the hypotenuse. This is one of the median. Why is that so? Because this is a right triangle. We are able to construct a circle of length C over 2. And the center of this circle is at the midpoint of C. So we have this side and the distance from here to the other vertex and the distance here are all equal to C over 2. So because this side and this side are equal, this angle and this angle are equal. And this angle is equal to this angle by similar triangles. Therefore, this angle and this angle are equal. And in this way, this line is symmetric to the median with respect to the bisector. And furthermore, even though we know this Symmedian, where is the Lemoine point, it's easy to prove that the Lemoine point is exactly the midpoint of the altitude on the hypotenuse. So let me sum it up. For a right triangle, a Symmedian is the altitude on the hypotenuse. And the Lemoine point is the midpoint of the altitude. It's very easy to calculate PC, that is from the Lemoine point to the hypotenuse, is equal to the altitude length over 2. Because of the ratio PA over A is equal to PB over B, and it's also equal to PC over C. So PC is known, so PA and PB are also known. This is the result. We know H times C is equal to A times B, the area of this right triangle. So H is equal to A times B over C. So PC is this. Now, BB over B is equal to PC over C. We move B here, we have PB like this, PA like this. So we are almost done. Then let's see how the Pythagorean theorem can be proved this way. This is a given triangle. We use as an area B. And the larger triangle constructed by extending the side of the outer side of the squares, we have a similar triangle A1, B1, C1. This A1, B1, C1 is area A, and this is B, so the outer triangular ring is A minus B. So what we need to do is finding out what A minus B is. And how do we find the scaling factor rho? Now, because we know connecting these lines, we have the Lemoine point, let me call it K. K is the midpoint of the altitude on the hypotenuse. So PC is equal to AB divided by 2C, as we have seen. So for this triangle, KAB, the altitude on hypotenuse is PC, which is this one. For the triangle K, A1, B1, the altitude is the distance from K to side C1, which is equal to PC plus C. Because KAB and KA1, B1 are similar. Therefore, rho can be calculated as C over C1, which is also equal to the ratio of PC over C plus PC. Now, rho is also the scaling factor going from A1, B1, C1 to ABC, which means rho is equal to A over A1, B over B1, C over C1. Because we have already calculated PC, so rho is C over C1, which is the altitude of triangle KAB over the altitude of triangle A, KA1, B1. So we have PC over PC plus C, and then some simplification, we have this. From rho, we calculate 1 over rho divided by rho. Because rho is A over A1 equals B over B1 and so on. We have A1 is A divided by rho, B1 is B divided by rho, and C1 is equal to C divided by rho. Therefore, we are able to compute the area of these three trapezoids. So, the area of trapezoid AB, B1, A1 is equal to half of C plus C1 multiplied by the altitude. Because C1 is C over rho, we have this. The remaining two are calculated exactly the same way. So the sum of these three trapezoids is adding them together. We have a common factor. The only uncommon is A squared, B squared, C squared. So we have this. So the area of A1, B1, C1 according to our method is 1 over 1 minus rho squared multiplied by the area of sum of these three trapezoids. So we have 1 over 1 minus rho squared here, and this is the area of the triangular ring. So we factor out 1 minus rho squared to be 1 minus rho times 1 plus rho. So this one is cancelled. According to our method, area A1, B1, C1 is this. But the area can also be calculated as the product of A1 and B1 divided by 2. As we mentioned, A1 is A over rho, B1 is B over rho. We have this. So these two areas must be equal. We can take one rho out, and these two cancel out. We have this. Then we move 1 minus rho to the right, and we know 1 over rho divided by rho is calculated to be this. So here, A times B are cancelled out. We have 2c squared. This 2c squared can eliminate one of the c squared. We have A squared plus B squared equals c squared. This is possibly a new proof to the Pythagorean theorem. Now, there is even a simple one if we do not follow our method. Remember, this is right triangle. This is the altitude on the hypotenuse, and this is the Lemoine point, which is the midpoint of the altitude. So we have calculated PA, PB, and PC. So the area of this right triangle is the sum of these three smaller triangles. So because we know PA, PB, PC, like this, so the area of ABC is the sum of KAB plus KBC plus KCB, which is do it this way. Plug PC, PA, and PB in. After some calculation, we have this. And then the area of the triangle ABC is simply the product of A and B divided by 2. This is our method, and this is the obvious method. So this term canceled out immediately. We have 2c squared here, move to the right. This 2c squared cancels one of the c squared. We have the Pythagorean theorem. So what did we learn? First, similarity and its scaling factor provides an interesting way of computing the length of a line segment and the area of a shape. This area offers a new approach to revisiting proofs of the Pythagorean theorem. We took several old proofs from Loomis' book and also offers a new proof. With the help of Lemoine or Grebe or Symmedian points, we have a new and short proof of the Pythagorean theorem using this new technique. Here is the reference. Cut the knot is available here, which is example we discussed earlier. And the new construction of the Lemoine points was taken from this book. And the ratio of the distance to each side, or equal, is taken from this book. Furthermore, we refer to Loomis' book several times. This is the book, and you may be able to find a PDF scanned version here. This is the end of our discussion, in which we offer you a new way to prove the Pythagorean theorem. The next episode, the third one, we will discuss Miss Jackson and Johnson's proof. Miss Jackson and Miss Johnson are teenagers, high school girls. So it's a wonderful event when they present their results at the AMS conference. We will prove it without the use of trigonometry. We also discuss their trigonometry proof. So it's the end of this episode. Hope you follow my lecture and hope to see you next time. Goodbye and good luck.